Okay, so our tour continues with Turing Award winner Barbara Liskov, who's a longtime professor at MIT, and I believe their first female PhD graduate in computer science ever, and possibly the first PhD. And a UC Berkeley alumnus. And a UC Berkeley alumnus. Well, that's obvious. That's where, all the source of all good computer science bits. No, so the Liskov substitution principle is based on her seminal work in abstract type theory, and the idea that you could not hide data in such a way that you could reason about types and subtypes according to the following lemma, that a method that works on an instance of type T should also do the right thing on any subtype of T. And I actually remember being in the audience shortly after she was given the Turing Award. She made a keynote speech at a very widely respected systems conference. And I was sitting in the audience, the speaker was introducing her and was explaining a little bit about this basic idea that was the base, part of the basis for her receiving the Turing Award. And somebody behind me muttered, "Everybody knows that. Why would she get an award for that?" Okay, they missed the point. Anyway, do you guys see why that's it? Okay. All right, never mind. So we've been saying all along that Ruby is a language that doesn't really depend much on classes and subclasses. It's really more about what methods you respond to and duck typing. So that doesn't mean that the Liskov principle doesn't apply. It just means that we have to think about substitutability in a different way. It depends on how the collaborators are interacting with the objects. And as again, with all of these things, it's much easier to just jump into an example. So let us do that. So this is sort of a canonical example of what can go wrong if you violate Liskov substitution. Here's a straightforward class for a rectangle. It's got a width, height, and coordinates at the top left corner, and it's got methods like area and perimeter. Okay, not a problem. And now you try to create a square, which is just a special kind of rectangle, right? Except that it's really not, because a square has to have the same width and height. So now, whenever you set the width, you also have to set the height, otherwise it isn't really a square. But you're thinking, well, okay, I just override the setter methods and it still behaves like a square. I can still use area and perimeter to compute those properties of a square. So now here's a problem, right? If we add, this is a perfectly legitimate method to add to rectangle, right? Make the rectangle twice as wide as it is high. And now we've busted compatibility because there's no way that a square can do anything reasonable with this, right? So now we have the problem that you have a subclass that has a behavior in its superclass that makes no sense for the subclass. So what could the subclass do? Well, it could throw an exception, right? But that is kind of stupid because the whole point of being a subclass is like you're everything your superclass is, but also other stuff. So this doesn't make sense, right? And some people call this design smell a refused bequest. Your superclass has bequeathed something to you, like through inheritance, but you refuse it. You send it away. I think that's funny, but that's the kind of sense of humor I have. So here's a way to do it that, again, uses this principle of don't rely so much on inheritance. Instead, use composition plus delegation. So this is probably the nicest example of how to do it. So what happens now? We still have we're going to use our rectangle class as is. But now when we create a square, we'll make one of the components of the square be a rectangle that happens to have those dimensions. So now we can still do sensible things like setting the side of a square. We're not inheriting the width and height setters because a square is no longer a subclass of rectangle, right? This is important because if square was a subclass of rectangle, you would expect to be able to do anything to a square that you could do to a rectangle. And we just saw that there's cases where you could make that not be true. Now it's a separate class, so you don't necessarily expect that everything that applies to rectangles would also apply to squares. But if somebody tries to compute the area or the perimeter, we can still delegate those behaviors back up to the rectangle, right? So we include a rectangle so that we can reuse the behaviors that make sense to reuse, right? So the rectangle is a component of the square. We delegate certain behaviors back to the rectangle. So now we sort of get the best of both worlds, right? We get the reuse where we can take care of it. And for the parts that have really nothing in common with our superclass, well, we don't have a superclass anymore. So this is a LSP compliant solution, if you will, because we've avoided the problem of a subclass that doesn't know what to do when it inherits a behavior that makes no sense for it. Typically, when this arises is when you've used inheritance and you really shouldn't have, right? So there's many, many cases where there's a temptation to inherit, but really what you probably should do is composition plus delegation like we just did. And one way to test it is if you can't think about what is the consistent set of assumptions that form the contract between the class and its collaborators, right? If you have a contract that all of a sudden breaks down in the face of a collaborator because there's things that your superclass can't do anymore, and in the case of square, this was part of the problem, right? We had a square that could not meaningfully override this make twice as wide as high without violating the contract. Because what's the contract for a rectangle? That anything that works on a rectangle should also work on subclasses of a rectangle, right? There's no way for a square to live up to that contract if this is one of the things a rectangle can do. So on the right is the solution that we actually showed as the LSP compliant version. Square now is its own class, but it has a component which is a rectangle, and that component can be used to delegate some of the calls where you are able to reuse some of the functionality. A symptom that you run into if you're actually trying to make changes to your code and you find that you're making changes to a subclass and suddenly that requires changes to a superclass, that's a bad sign, right? Because the subclass is supposed to be a specialization or an extension of the superclass, not a contradictory replacement of it. So if you find that changes to your subclass requires changes to your superclass, some people call that shotgun surgery, like you're making changes in multiple places with a shotgun, that probably means that you misused inheritance and that what you were really, the reuse you were trying to achieve might be better achieved through composition plus delegation. So here's a question about that. In duck-type languages like Ruby, LSP violations can occur even when inheritance is not used. And here's another statement. In statically typed languages like, say, Java, if the compiler reports that there's no type errors and no type warnings, then there's no violations of LSP. So which of those statements, or possibly both, or possibly neither, are true?